Okay, so now you're with me, and I'm already here on the page. So we wrote down all our initial data first, right? And now we did this calculation. I mean, I've set it up. The rest is just scribbling and dibbling. Okay, we've done the physics. This is the physics part. Now, the second part. The second part is we have to for step 2. It's the second collision, and it's totally embedded. All right. So now for the second collision, the bullet becomes totally embedded in the block. All right. At some point, it's totally embedded in the block. But still, we have the momentum before is equal to the momentum after. All right. Now, so we've got M1 V1 naught, which we know because we know that V1 naught is equal to V1 final from step 1. Okay, carry that guy over. So now he's the initial, when he was careening towards, this is V1 final from step 1. That's the key. Well, that's one of the keys to the problem. Is plus mass of block 2 times 0, because it's just sitting there, is equal to, now it's completely embedded. Boom. It goes completely inside there. So these two guys are stuck together. Times V final of the second collision. We'll just call that V final 2. We already got V final 1 earlier of the first one. All right, so you know this. You calculated this earlier. This is 0. You've got these two guys. This is your only unknown. Not bad. Not bad. So now, I'm not sure which kinetic energy they want us to calculate, because there's the kinetic energy at the very, very beginning. Okay, kinetic. But I think they want us to calculate the kinetic energy here of this one and compare the two. So when it asks the question, find the ratio of the total kinetic energy after the collision to that before the collision. Okay, so I'm making the assumption that they're meaning right here, at the very end here. So that kinetic energy, so the kinetic energy before, and they show you how to set up the ratio. After divided by before. And it should be, I'm hoping it's less. And it's going to be a number. And it's going to just be a number, and I'm sure it's going to be less than 1 because it's an inelastic collision. So the before, you've got more kinetic energy at the start than you do at the end. All right? But it's not that hard to compute once you get, so the kinetic energy before is M1 of the block times its initial velocity, 1/2 squared. Okay? The kinetic energy after, the final kinetic energy is 1/2 of what? This guy. M1 plus M2. And I'm going to show you something else that's kind of funny, times V final 2 at the very end squared. So you're going to put those over each other. Okay? Now, sidebar. One other thing. You can represent, if you find this momentum here, if you go ahead and calculate this momentum here, here's another formula for kinetic energy. Kinetic energy is equal to the momentum squared divided by 2m. That's a fancy way of writing it. That's the way physicists write it. Because when we start dealing with very small particles bouncing around, careening off each other, and then sometimes we'll just have the momentum of a photon, we have to write it, and it doesn't have any mass or an electron. I mean, and then we start using electron volts and the electron volt mass of things. this is the way we write it. And it'll work in classical too. So if you want to get fancy, you can do it that way. All right, listen, I'm going to look at one more problem, and we'll might look at some of them in class even. All right, out of here.